So we went over part A already, and we're going to take a look at part B right now. So part B says evaluate the integral of g of x dx from 1 to 6. And that's going to be 1 over here to 6. The issue with this is we've got a function for 3 to 6, and we've got another graph, like we already know the function for 3 to 6, and we've got this piecewise linear portion going from 1 to 3. And integrating all that in one integral seems kind of messy. I don't really want to figure out both of the functions and combine them. And the best way to do this seems to be to break it into two integrals. So we'll say the integral from 1 to 6 g of x dx is equal to the integral from 1 to 3 g of x dx plus the integral from 3 to 6 g of x dx. And I'm going from 1 to 3 with this piecewise portion, and 3 to 6 with this quadratic portion. So the area from 1 to 3 is just going to be a 2 by 2 square. Is 2 times 2. That's convenient. And then this next integral, we're going to plug in the function g of x at that in that range from 3 to 6. So that's going to be from 3 to 6, we're integrating 2 times x minus 4, the whole square dx. So that's going to give us 4 plus, let's see, so integrating, I'm going to take that 2 out, 6, x, oops, and we've got x minus 4, the whole squared dx, and it's great on the FRQs to write down every single step and show all your work. Okay. So with this next segment, what we're going to do is we're going to integrate this portion, right? And that 2 is always going to be on the outside, but I don't really want it to involve it right now. So if you remember, using the power rule, we can x minus 4, and we're going to add 1 to the exponent, and we're going to write the exponent as a denominator, multiplied by the reciprocal of the exponent. So that's how the power rule works. And if you take the power rule for the derivative on this, if you differentiate x minus 4 cubed over 3, you're going to get d dx. You get 3 over 3 times x minus 4 squared, which works out perfectly. So coming back, we've got this evaluated from 6 to 3, right? And we can write this as 4 plus 2/3 times 8 minus 2/3 times -1. And I'll just save you the hassle of going through and plugging in 6 and 3 into that. And that gets us to 4 plus 16/3 plus 2/3. And adding that up, we get 18/3 over here, which is just 6. And so we end up with 4 plus 6 equals 10. So the integral from 6 to 1, evaluated from 6 to 1 of g of x dx is going to equal 10. And that's your answer for part B. So moving on to part C, let's take a look at what they want here. They're saying from -5 to x is less than x is less than 6. So from the interval from -5 to 6, this whole thing they've provided us exclusive. On what open intervals, if any, is the graph of x both increasing and concave up? So when the graph of f is increasing, we take a look at the first derivative. We say f prime of x is greater than 0. When it's concave up, to look at concavity, we look at the second derivative. We say f double prime x is greater than 0. And just as a quick refresher, decreasing would just mean f prime of x is less than 0, and concave down would be f double prime of x is less than 0. So coming back, if it's both increasing and concave up, it needs to fulfill both of these conditions. So let me just find all the places it's increasing, all the intervals it's increasing on, and then see which of those intervals it's concave up on. So in this case, f prime of x is going to be g of x. So we're just going to take a look at the values where g of x, so f prime of x equals g of x. So we'll look at the values where g of x is greater than 0. That's just where it's positive. And so that's going to be all the way over here. So from 0 to, what is that, 4, and 4 to 6, right over here. All right, and now, however, I just want to take a moment and notice that we've got two intervals. We're not going straight from 0 to 6, and that's because it's 0 at this point. That does not count as a positive value, so make sure you're breaking it into two open intervals. Okay, so our next step is going to be checking for concavity. We already know where it's increasing, but where is it concave up within this interval, or rather these two intervals? So where it's concave up is where g prime of x is greater than 0, or rather the slope of g of x is greater than 0, or it's positive. So over here we got a positive slope. We have a positive slope from 0 to 1, and then when it flatlines, so I'll just write down 0 to 1, then it's a flat line with a slope of 0. That's not positive. Then it's a line with a negative slope. That's not positive. And then we have a positive slope up here where it's increasing. So over here, g of x is increasing, which means g prime of x has got a positive value. So let me just write down 4 to 6. All right, and so let's compare these two intervals and see where there's an overlap. So I see 4 to 6 and 4 to 6, so I know certainly they're going to be increasing and concave up on 4 to 6. And then I also see 0 to 4 and 0 to 1. 0 to 1 falls within the interval of 0 to 4, so it's just this part as opposed to this whole part. So that's the overlap we're going to count. So we're going to say that it's on the interval 0, 1 union 4, 6, f is both increasing, and I would spell it out on the test, and concave up. And this is an important part because you guys are going to need to write a because on the exam. Because f is increasing on that interval, or let's say f and g are both increasing. So f is increasing, and so is g, which means f and f prime are increasing, meaning that f double prime of x is greater than 0 and f prime of x is greater than 0. So you don't really have to say f and g are both increasing, but you do need to say f double prime of x and f prime of x are both greater than 0 and specify that because you need that justification. It's on the rubric for the grading. So part D should go pretty fast. Find the x-coordinate of each point of inflection on the graph of f. Give a reason for your answer. So again, they want you to give that because justification. So this is important. But what is a point of inflection? A point of inflection is where concavity changes. So it goes from concave up to concave down, or vice versa, concave down to concave up. And what that means is the graph goes from increasing to decreasing, or decreasing to increasing. Because G equals F prime, that's why I said it goes from increasing to decreasing, or decreasing to increasing for G. So the slope is going to change in that way, whereas the original graph of F would change here. Now, we don't have the original graph of F in front of us, but we do have G. So we need to look for any point where the graph goes from decreasing to increasing, or increasing to decreasing. And so that's not it. That's not it. It's just the slope is 0 here. It's increasing and then the slope is 0 here again. But hold on, it's decreasing here and the slope of g is increasing, which means f double prime is positive. So f double prime goes from less than 0 to greater than 0 over here, which means that at 4 is a point of inflection of the graph f of x. And that's because f prime of x equals g of x switches from increasing to decreasing. Oh, my bad. From decreasing to increasing, actually. It goes from decreasing to increasing. So f double prime of 4 is where f double prime of x changes signs. So you're going to want to really have a solid justification tying together f of x, which is what they want you to find a point of inflection for, to g of x, which is the graph you're given, to f double prime of x, which is the second derivative test we can use in order to find that point of inflection.